Okay, let's get started. Let's talk a little bit about the weekly reports. Weekly report number 2 is due this evening. I promised you that we would talk about report 3 today. I didn't have time this morning to put it together, so we will talk about report 3 on Friday, and it will be due then the following Friday. So you got a little bit of a breather in terms of HCI between today and Friday, unless you don't need a breather. Okay, I'll take that as assent. Okay, so we'll talk about the weekly report 3 on Friday, and it'll be due on the following Friday, which will be the last day of class. And next week we will also talk about final presentations and oral presentations, which will be during the exam period. In case you forgot, there's no final exam in this class. Okay, any questions about weekly report number 2? No? Okay. So we're going to finish our section on looking outward today, talking about technologies that exist somehow out here in the physical world with us. And then on Friday, we will start in on our last theme, which is made up of 4 lectures, which is sort of looking inward, right? So talking about interactive technologies that are more tightly intertwined with us, including in lecture 27 and 28 when they are actually intertwined with us. Okay, so we ended last time by talking about robot-robot interaction, where from the point of view of an embodied and situated agent, such as a robot, it's moving about in its environment, and there are other things out there in the environment, including other robots. And we ended last time with this brainstorming session on trying to design modular robots for finding human survivors in a disaster site. In the interest of time, I think we're going to leave that brainstorming session where it is, and we'll start in on lecture 24, which has become known as the Twitch Plays Robotics project. So this was a project carried out by one of my graduate students who actually took this class a couple years ago. And in order to understand this project, we're going to go back to human-robot interaction. So we have our robot R, which is interacting with its environment. The robot is acting on its environment and sensing the repercussions of that action. But our robot is also interacting with humans, where humans act on or say something or influence the robot somehow. The robot senses the interaction with the human. The robot then acts in response to the interaction with the human, and the human senses the action of the robot. What happens if instead of a robot that's interacting with a single human interlocutor or another human, what happens if there are a huge number of humans that are collectively interacting with this one robot? So in the Twitch Plays Robotics project, we're going to look at Joey's work where she set up a robot or robots that are interacting simultaneously with many humans. And why might we want to do that? And again, we could do this for lots of reasons. In this case, Joey wanted to try and attempt to see whether we could recruit a crowd to help teach robots language. So a lot of what you're going to see today draws on some of the things we've already seen. You might remember the Human Speech Home project with Deb Roy, where they instrumented their home for the first 3 years of their child's life. This is going to be similar in the sense that we're going to have a lot of humans that are observing and influencing a robot, and we're going to record everything about those interactions in a way to see whether the robots are able to start to learn human languages. And we did this on the internet, so not surprisingly, the first language that a robot started to learn was English. And I'm going to walk you through lecture 24 here. It's a PDF today rather than a PowerPoint. There's a lot of embedded videos in here. I apologize, you probably won't be able to play them if you download the PDF, but I'm recording the lecture, so hopefully we'll be able to capture all the videos and you can go back and watch them at your leisure. Okay, so the slides for today actually came from a presentation at a conference we gave last summer, and the title of the paper was Robots Can Ground Crowd Proposed Symbols by Forming Theories of Group Mind. There's a lot of jargon in there, and as we go, we're going to unpack what these things mean. But for the moment, the basic idea is assuming that a large number of people can speak to a robot while that robot is interacting with its environment, can the robot learn that certain interactions that it makes with the environment, like this, whenever the robot interacts with its environment in this way, the crowd seems to emit a particular word, which is GRASP. So again, our robot knows no language whatsoever, but it starts to learn that that particular symbol, grasp, or that string, corresponds to this particular action. When the robot does something else, then another symbol starts to emerge from the crowd, which is PUT, or put. So the robot is going to try and ground or put these symbols, or understand what these symbols mean by relating them to its own experiences with the world. That's the executive summary of the Twitch Plays Robotics project. Okay, so before we get into the details, just a little bit of background. As you all know, we're in the middle of the big data revolution. If you trace the roots of this revolution, they date back to about 10, 15, 20 years ago. And one of the beginnings of the big data revolution was this particular game. Does anybody remember playing this game? Anybody know what this game is? No? Oh, there you go. It is becoming truly historical. So this was the ESP game. So the idea here was you'd go to a web page and you'd be shown an image and you'd be randomly matched up with some other player out there on the web, and all you were asked to do was type in keywords that described what you saw in the image. And whenever there was a match, so down here in the bottom right, both players happened to type in the keyword birthday, and the computer records that match. So these are two independent people out there on the internet, and they both use the same symbol, BIRTHDAY, for this image. So that symbol became associated with that image. The ESP game was played by millions of people against millions of images, and slowly this big data set started to emerge, where you had millions of photographs and tags for those photographs, which had been tagged by collective agreement of the crowd. So since the ESP game, there's been lots and lots of games like that, or other websites that, perhaps unbeknownst to the user, are tagging images and video and so on with the symbols of human language, which has now led to the machine learning revolution and the AI revolution, where now we have cameras that can recognize faces and images and so on, and a lot of it dates back to this early work. That's the big data revolution. As a roboticist, we're interested instead in the big action revolution, which has not yet occurred. The idea would be to try and create big action data sets where now you're associating the symbols or the words of human languages not necessarily with images and video, but with actual sensor motor experience. So from the robot's perspective, these robots might start to learn what these words mean, because these words are spoken by the crowd whenever the robot does one of these particular actions. These big action data sets do not yet exist. So like the ESP game, which helped us to create this big data set, can we create similar games around robots to start to develop this big action data set? That's the motivation. So far, so good? Okay. Okay, so here's our hypothesis that we're going to try and test. Can the crowd, if we create the right kind of interface to allow the crowd to interact with robots, can the crowd teach robots human languages in a data-driven, open-ended, and scalable manner? So again, we'll work our way through these three adjectives. But basically speaking, we're going to do this in a data-driven way. We're not going to start with hypotheses about how human children learn languages and try and build in those theories. No theories, just data. Very much like Deb Roy, let's just collect a whole bunch of data and see whether the robots can learn language, and not allow our theories about how humans or robots learn language to get in the way. We're going to do this in an open-ended manner, which you're going to see in a moment. Open-ended in the sense that we're going to connect the crowd with the robots, and the crowd can try and teach the robots any language they want. There aren't specific symbols that we are restricting the crowd to. And we're going to try and do this in a scalable manner so that as time goes on, we can add more and more robots, place them in more and more complex environments, which hopefully will enable the crowd to teach the robots more and more sophisticated language. That's where we're headed. Okay, so before we can test this hypothesis and show you the experiment, let's talk a little bit about language. We've talked about embodied cognition already, and if you remember back to the example with the photograph of Marilyn Monroe, we talked about computer vision, and I showed you the non-embodied approach to computer vision, which is supply a computer with millions of photographs with and without Marilyn Monroe in it. The computer learns to distinguish between the two sets. And I showed you the embodied approach to computer vision, which was BabyBot, which would reach out and physically interact with objects in its environment. So in the same way that I showed you the non-embodied and embodied approach to computer vision, let's talk about the non-embodied and embodied approach to teaching computers language. The non-embodied approach has been around since the 1970s. This is a particular project called the Psych project, which has been around since the 1980s. Psych for encyclopedia. And the basic idea here is give computers every piece of written text ever written by humans, and eventually computers will learn language in that way. The basic idea behind this is in all text corpora or all written documents, there are, of course, a number of symbols. And you can start to recognize that there are certain relationships between them. So as you're reading, you might see the sentence, Bill Clinton was a United States president. X was a Y. You might start to learn that this symbol called is indicating a particular relationship between this symbol and that symbol. So basically in the Psych project, what computers are trying to do is to take patterns that are sensed in the data, in the text, and learn relationships amongst them. There's a problem with this approach, however. What's the problem? Is this how you learn language? For those of you that speak another language other than English, is this how you learned it? Imagine you were learning a foreign language, and I gave you an English foreign language dictionary, and there's a particular word in the other language you don't understand, so you look that word up in the English foreign language dictionary, and it says X is an instance of Y. That's the definition of X. You don't know what Y is, so you go to a different part of the dictionary and look that up, and it says Y is defined as W and Z. You don't know what W and Z is, so you go back to the dictionary, you look up the definition of W and Z, and if you keep going, eventually something will say Q is an instance of X. But you're still eventually trying to figure out what X means.
So, do you mean like the relational matrix or matrices between different types of information isn't yet formed?
You're trying to learn those relationships, right? So there's some word you don't understand in a foreign language, and the dictionary tells you this word is related to these other words in a particular way, but you don't know what those other words are, right? That's in essence what a computer in the Psych project is trying to do. In essence, you end up going around and around in a loop, right? Your only understanding of this symbol is how it relates to other symbols, which you partly or don't understand. Okay, that's the non-embodied approach. So if you're trying to learn a language by learning the symbols of that language, but they're being related to other symbols in the language, you keep going around and around and around. How do you break this vicious cycle? The idea is in order to break this vicious cycle, you need to ground things somehow. You can't keep going around in the air relating one symbol to another. It needs to be grounded in some soil to get you started. Once a few of the symbols are grounded, meaning you understand what those symbols are, then you can start to connect other symbols to the symbol that's grounded. That's known as the symbol grounding problem. How do you actually ground it? Well, in the embodied approach to teaching machines language, we're going to ground symbols in this, the sensor motor experience. So let's say one of our robots is jumping around and it's doing its thing, and it hears from the crowd the symbol JUMP, and it happens to hear this word whenever the pressure on the soles of the feet of the robot are high and then they suddenly drop. Remember that the robot does not speak any English whatsoever, but it can feel what's happening as it moves around in its environment. And like BabyBot, where when it did something, it would see something occur, right? It would see this blob that was in the shape of an apple would start to roll. That contingency, if I do this, then I see this happen. In the same way that the robot learns that if it does this, it hears this particular symbol from the crowd. If it hears that, or it senses that contingency enough, whenever this happens, I tend to hear this, and it starts to connect that. If you were able to ask the robot what JUMP means, the robot would tell you, maybe not with English, because this is the only word of English it knows yet. If you were to ask it what jump means, the robot would jump. It's showing you that it knows what jump means. Jump is a very motoric word, meaning if you think about the word jump, it's very clear how it's connected to an actual physical experience you have with your environment. So we could start to think about how motoric words like jump, push, grasp, place on top of, those kinds of motoric words that are very close to actions could be grounded in a robot's or a human's experience. But how would you ground the word socialism? Socialism is a very abstract word. It's not very motoric. The robot might, if it starts to ground motoric words like jump, it might then be able to recursively ground slightly less motoric words in the more motoric words. So the robot might learn that whenever it does this, it always hears jump, but there is a larger class of things it can do that get the crowd to say this. So whenever the robot is moving, whenever it's doing something other than standing still, it tends to hear this. This is a harder thing to ground in particular experiences because there's a broader class of these actions that cause the crowd to say this. But maybe it starts to learn that, okay, I hear this whenever I'm moving, and I hear this during very specific movements. So therefore, this thing, JUMP, must be a particular instance of this broader class movement. This is the vision of an embodied approach to language acquisition. We don't have robots that do that yet, so we're working on step one. Can we get robots that can ground these motoric words? And if they do, maybe we can gradually start to teach them how to ground increasingly abstract words. So far, so good? Okay, so how do we get the crowd to do this? Well, we need to create an interface through which the crowd can try and teach the robots language. We did this by creating a website on Twitch. Twitch is a website through which millions of people watch other people play video games. This was a real eye-opener to me when one of my students introduced it to me, but we could see the potential of this idea. So a typical Twitch channel, you're playing your video game at home, you live stream your video game to Twitch, and other people watch you play it and comment on you while you're playing it. In our case, instead of live streaming a video game, we run a robot simulation here on campus and then stream that simulation live to a Twitch channel. And then on the right here, we have the crowd watching the robot and commenting on what the robot is doing. Okay, I'm just going to pause this for a moment. So that's the interface through which the crowd is able to watch the robot and talk to the robot. That's step one, which is act. So the first thing the robot has to do is do something to provide the raw material to get the crowd thinking about what kinds of language they might be able to teach the robot. So I'm going to now go through the details of the Twitch robotics project. I don't expect you to remember all the details, but to summarize this up, there's 4 steps. The robots are going to act. The crowd is going to observe those actions. So here's the crowd observing the robot. When they're observing, they're going to try and talk to the robot. So the robot is going to collect a huge amount of this stuff and this stuff, the words emitted by the crowd. In step 3, the robot is going to use a machine learning algorithm to try and find correlations between this stuff and words. Right? I just gave you one example, which is the robot might learn that whenever the pressure at its feet drop, it always hears the word jump. It might learn that relationship. So that's step 3. The robot is going to try and learn. Then, in order to prove to us that the robots are going to try and prove to us that they have managed to start to learn English by predicting what the crowd is going to do. So when the crowd asks the robot to jump, and the robot actually jumps, the robot is going to predict what the crowd is going to do. And in that case, the robot would predict that the crowd is going to say, "Good job, you did the right thing." If the crowd says jump and the robot doesn't move, again, if the robot has learned what jump means, the robot should be able to predict that the crowd is going to say, "We asked you to jump, and whatever you're doing, that's not jumping." That's the measurement, the yardstick we're going to use to try and prove which aspects of language the robot has learned. If it hears something and it on purpose disobeys the command, it should be able to predict that the crowd will say thumbs down. So the robot knows what jump means in that sense.
What sort of sample size? How many people were you able to get?
Okay, how many people were we able to get? I will show you in a moment. Okay, so that's the basic idea, right? So robot acts, crowd observes, speaks to the robot tries to learn relationships between language and action, and then to prove to us that it's learned language, it's going to predict how the crowd responds when it does something. So far, so good? Okay, so you're raring to see the actual data. Okay, I'm going to walk you through this in 1, 2, 3, 4, 5, 6 steps. So what I just showed you in the video is we have our robot simulation running here. It's running continuously on campus. We're broadcasting the feed to Twitch channel where people are watching it. The master program is watching Twitch, so this is just a Python script we wrote that is capturing all of the chat that the crowd emits and storing it in our database. So this loop just continues running indefinitely where robots do things in simulation, the crowd watches the robots do things on Twitch, and we capture the crowd's responses to those actions in a database. Okay, so here we go. This might be a little bit difficult to see in the video. Here's our robot, which is doing something. In the let me speed this up a little bit. In this top right panel here, the crowd is voting on what word or words to teach the robot next. At this moment, one member of the crowd has requested that we teach the robot crawl forward. Someone else just voted for walk forward. And if I speed this up a little bit, maybe there'll be a couple more votes. Okay. There was another vote for walk forward. So the crowd is at this point voting on which word or which phrase to teach the robot next. We do this vote on a 3-minute period. So for every 3 minutes, the crowd can just type in arbitrary words, and whichever string is in the majority, that's the symbol that we try to teach the robots during the next 3-minute period. Okay, so what just happened is that 3-minute period ended, and in this lower right panel here, again, you probably can't see this very well, the current symbol that we're now sending to the robot is the command walk forward. So all the robot gets is this string walk forward. As it's moving, you'll notice that in the top right panel, the crowd is voting for what to teach the robot next. And in the bottom right panel here, we'll wait a little bit, the crowd is voting for VY or VN. VY means violet robot. Yes, you're obeying the command walk forward. VN means violet robot. No, you're disobeying the command walk forward. So we told the crowd when they came to this site to think of the robot as a pet. We're trying to teach this robot things. We don't know what things this robot may be able to learn and what things it may not be able to learn. It's up to the crowd to decide what they want to try and teach it. So in essence, the crowd is deciding two things. What symbol are we going to send to the robot? And once you decide on what symbol, which in this case is walk forward, now you're going to reinforce the robot. You're going to say thumbs up, yes, if it's obeying the command, thumbs down if it isn't, and we're collecting all of that information. So far, so good? Okay. All right, here's what our database looks like. We did this experiment with the simple worm robot that you just saw, and simple worm robot, which is R0, and a second robot, which is this quadrupedal four-legged robot. And every 3-minute period, every hour, we switched the robot. So for 1 hour, it was the worm. The next hour, it was the quadruped. Third hour, it was the worm. Back and forth, on and on. During that period, at every 3-minute interval, we sent a new command to the robot. So uppercase R stands for robot, uppercase C stands for command. So during any given hour, we get a whole bunch of commands emitted by the crowd. So down here, CIJ indicates the jth command that was sent to the ith robot. So for each command, which is in existence for a 3-minute period, we send a number of controllers. So a controller is a little neural network that sits inside the robot and causes it to do something. You can think of this, the controller as the brain of the robot. During any one 3-minute period, we send 6 brains for 30 seconds each. So the robot does 6 different things underneath any one given command. So we have an hour cycle where we're changing the robots, a 3-minute cycle in which we're changing what we ask the robot to do, and inside each 3-minute cycle we have a 30-second cycle where the robot is doing different things and watching whether the crowd says, no, you're not obeying the command, or yes, you are obeying the command. So far, so good? So robots, commands, controllers, and then finally, during a single 30-second period, when one controller is in charge of the robot, we collect the number of thumbs up, which is S1 here, and we also count up the total number of thumbs down, which is S0. That's our database. Okay. Here it is on fast forward, so you can get an idea about how this worked. We ran this for about 3 weeks, but most of the traffic we got was in the first 24 hours. This is kind of how things look. So you can see a whole bunch of different controllers. In the top right, you can see the crowd voting for different commands. In the bottom right, you can see the crowd saying thumbs up or thumbs down. And here's the chat window where the crowd is actually typing in what they want to try and teach the robot, and yes or no. Okay, on to the actual data. So we had thousands of people actually watch the stream, but only 424 of them actually typed something into chat. So we've got H1 through H424 here. There were 57,000 evaluations or controllers. So the two robots did 57,000 different things. Only 6,000 of those were ever commented upon by the crowd. So most of the controllers, the crowd said nothing. So the robot has no feedback on whether it was actually obeying or disobeying the command. And over this 3-week period, the crowd typed in over 16,000 pieces of chat. I mentioned that we tried to keep this open-ended, so we didn't tell the crowd what to try and teach the robot. The crowd typed in almost 9,000 commands in total, and among that set there were 266 distinct commands. The most common one was jump, which was typed in 385 times, followed by walk forward, move forward, run, and then crawl forward. Those were the top 5, but there were a total of 266. What other words do you think appeared in the rest of this list? Other directions, right? So there are a lot of other motoric words, right? If you note here, again, the crowd could type in anything they want. These are very motoric words. They're close to physical experience. Does anybody remember, was it a month or 2 months ago, the Microsoft chat bot that went horribly wrong? That's a hint. What else do you think is in this list of 266 commands? Really offensive things, and every possible misspelling of those really offensive things, absolutely. When you learn a foreign language and your foreign language friend helps you learn it, what are the first few words you learn? Right? Okay, so we counted that as a plus, right? The crowd is teaching the robot as they would teach anyone trying to learn a foreign language. All right, lots of swear words, lots of very offensive words. Someone asked the robot to prove Fermat's last theorem. That was a good one. Not very motoric, at least not how I see it. But again, this was in the long tail. It was one of the rare commands. Some people asked the robot several times to be yourself. It's an interesting run, right? That one we're on the fence of. Is that a good one or not? What else was in there? All sorts of crazy things. Okay. However, again, the things that bubbled to the top, the things that the crowd said over and over again, were these very simple motoric words. So if you remember back to Deb Roy's experiment, we looked at that curve that had the dip in the middle, that the parents seemed to be simplifying their language when their child seemed to be on the verge of emitting the adult form of that language for the first time. Professor Roy claimed that that was because the children were scaffolding the parents at the same time that the parents were scaffolding the child, right? So part of the inspiration for this project came from that set of results. Would the crowd, without us telling them to do so, would they spontaneously try and scaffold the language learning of the robot? Would they make things simpler for the robot? A few users absolutely didn't, but in general, they did. Okay. So that's commands, the symbols that the crowd signaled. Then there's the reinforcement signal. So reinforcement, positive reinforcement is thumbs up. Negative reinforcement is thumbs down. We got a total of 7,500 thumbs up or thumbs down. On average, the 6,000 evaluations up here are the 6,000 controllers that the crowd did respond to. Each one of those 6,000 got, on average, a little more than one thumb up or thumbs down. Sometimes the robot would do something and the crowd would give 3 thumbs up and 2 thumbs down, or one person would give 1 thumbs down, or the crowd would be completely silent. Right? Okay. Among the 424 subjects, on average, they gave a total of 17 thumbs up or thumbs down. The proportion of positive reinforcement, which goes between 0 and 1, the average came out to 0.28. What does that tell you about the crowd's overall reinforcement of the robots?
Pretty low.
Pretty low. Most of the time, thumbs down, right? Which you would expect. The robot doesn't speak English, and like the Kismet robot, our robots are just moving randomly. They're not changing how they act based on what the crowd says, just random actions. Okay, so that's the data set. So now we're going to move on from act and the crowd observing and responding to learning. So now we're going to try and get the robot to try and ground some of these symbols. We took the most popular symbol, jump, and we tested that one first. Can we get the robot to ground this symbol, jump? So we took jump up here, and we went into our database and we collected all of the N's, which are all of the controllers that were executed under the command jump, and there turned out to be about 1,300 actions or 1,300 controllers that were executed under the command jump and that received at least one thumb up or one thumb down, right? So if there was a controller executed under the command jump and the crowd didn't say anything, that's not very useful to the robot. Okay, so that gives us 1,300 of these N's, these controllers. We took all 1,300 of those controllers and we dropped them back into the robot, and the robot did exactly the same thing that it did before. This time, however, when it executed those 1,300 controllers, we recorded a matrix called T, which is the touch information. So in the little worm that you see here, the worm is made up of 3 segments. We put one touch sensor in each of the 3 segments, and then as the robot moved, if that segment was in contact with the ground, that touch sensor would fire. If the segment was off the ground, the touch sensor would not fire. So we get binary information back. For one of those controllers, as the robot did its thing for 30 seconds, we recorded that touch information into a matrix that has 3 columns, 1 column for each of the 3 touch sensors. What do you think the rows in this matrix correspond to? So we take one of these 1,300 controllers, we put it in the worm robot, we put the worm robot in the simulation and turn it on. The moment we turn on the simulation, one or more of the segments touches the ground. We take those 3 numbers, those 3 binary numbers, and we store them in the top row of the matrix. The robot moves, right? It acts and gets some sensory information back. It acts again, gets another 3 numbers back. We store that in the next row, the second row. The robot acts again. We take the 3 touch sensors, store them in the 3rd row, and keep going. So each column corresponds to one of the sensors, and each row corresponds to one time step in the simulation. So the matrix as a whole is a record or a memory of the robot's experience with that controller. So far, so good? Okay. So for every controller Nijk, so the controller that was executed on the ith robot, either the worm robot or the legged robot, we have J. In this case, J is a command, just one command, which is jump. And K is that particular controller, one of those 1,300 controllers. So associated with each of those 1,300 controllers, we have a matrix T, which was the robot's experience using that controller. And we also compute O, which is the crowd's response to that particular controller. And I won't go through the math here, but again, O is this number that ranges between 0 and 1. 0 means, for that particular controller, everybody said thumbs down. An O of 1 means everybody gave a thumbs up. An O of 0.5 means 2 people thumbs down, 2 people thumbs up, or 3 thumbs down, 3 thumbs up, doesn't matter, right? Split vote. So far, so good? Okay, that's the data that we collected when we replayed these 1,300 controllers. Let's have a look at what this data set looks like. This is the data set for just the worm, and there were about 700 of these and about 800 for the legged robot, which sums to 1,300. Okay, each dot here corresponds to one of those controllers. The horizontal position of each dot is a function of that matrix T. So how much time did the robot spend on the ground? If every single element of a matrix T had a 1 in it, then that dot would have a position of 1. If half of the elements in that matrix are 1 and the other half are 0, then the robot spent half the time on the ground. I didn't explain that well, I apologize. They didn't just take the average. It was the fraction of rows that were all 0. So if a given row had all zeros, that meant the robot was off the ground, right? So if all the rows had all zeros, that means that the robot spent, 0 over here, it spent all the time on the ground. If all the rows had at least one in them, then the position would be over here. Sorry, I didn't explain that very well. Is that clear? Okay. The vertical position of a dot is the crowd response. The higher the dot is, the more positive reinforcement that particular controller got back. That's the data. What's the dashed line representing here? The correlation, right? So is it a correlation here or an anti-correlation? It's anti-correlation, right? So the more time that the robot spent on the ground, when the robot heard the command jump, the more the crowd said thumbs down, which is what you would expect, right? So again, this was good news. This meant that despite the fact that there were definitely a few users on the site that were abusing it, most of the time the crowd was doing more or less what we asked them to do. They were trying to help the robot learn what jump means. Here's the same data, but now plotted for the legged robot. And again, we see an anti-correlation. So both the worm robot and the legged robot are going to learn what jump means. From the point of view of these robots, jump means the more time that at least one of my touch sensors is firing, the less the crowd thinks I'm doing the right thing. The more rows in my T matrix that are all zeros, the more the crowd likes it. That's what jump means to me. Jump might mean something very different to us, but for the robots, that's what it means. So for both robots, they have a similar understanding of the word jump, but it's similar but not identical. Same anti-correlation, but slightly different, which was another interesting thing we found from this experiment, that what jump means to a robot is dependent on its body, how it's actually built. So this robot over here thinks jump means something slightly different from this robot. What's the difference? Imagine these robots could talk and you ask them to explain what jump means to them. They would give you a slightly different answer. What would they tell you?
They propel themselves upward differently because one will do it from his legs and the other has to do it from his torso. Absolutely, right? So for the legged robot, it's able to jump higher or stay in the air longer. So for it, jump means something a little bit more athletic, right? For the worm robot, which has a harder time getting off the ground, it still knows that jump means be off the ground, but according to the worm, it means be off the ground for less time, right? So a similar meaning, but not quite the same thing, right? So this is important for us as roboticists, because if we want to build robots that can talk English or talk to humans in natural language, are robots going to understand our words in the same way that we understand it, right? If a robot were to observe us jumping off the ground, and we were to ask a robot, is that person jumping? What answer would the worm robot give? What answer would this robot give? If we try and teach robots that don't look anything like us, are they going to ground symbols in the same way that we do? Hard to say. Okay, so what I've shown you is the data for jump, and I've shown you the regression line, which is a very, very simple model, the simplest possible model that the robot could use to ground these symbols. We went one step further as we set aside regression and we used a machine learning algorithm. In this case, we used an artificial neural network, which we've mentioned again in this class, and I'm not going to go into the details. But the neural network basically takes as input
it takes as input the T matrix. It takes one row and digests it. Then it takes the next row and digests it, and the next row, and the next row, and the next row. It digests one of these T matrices, and a single number appears at the output of this artificial neural network at the end of digesting one of these T matrices. What do you think that number represents? So the robot is trying to learn what jump means. It takes the T matrix, it feeds it into its neural network, and a single number appears at the output. What do you think that number is?
Is it just correct or incorrect?
It's not correct or incorrect because the robot doesn't know yet what the crowd said. It doesn't see the thumbs up or thumbs down yet. All we've given it is the T matrix, and it outputs a single number. What do you think that single number represents? What is the robot trying to tell us with that single number?
Prediction about the response.
A prediction about the response, exactly. So if we feed in a T matrix and the number here at the output, which can range between 0 and 1, if the output is 1, what is the robot telling us? It's a prediction. What does a prediction of 1 mean?
They'll positively reinforce the
The robot says, I'll bet you that everyone said this when I did that T matrix. If the output is 0, what is the robot telling us? It's saying, I think everybody thought I was disobeying that command. Right? However, the robot doesn't know anything yet. We're just starting, right? So a random number appears at the output. We compare that number to the actual reinforcement. If the robot outputs 1, meaning it thinks everybody gave thumbs up, but in fact everybody gave thumbs down, the robot's prediction is incorrect. And you know by now what we do to a machine learning algorithm when it makes an incorrect prediction. We go back and make some change to this neural network so that instead of outputting a 1, which was wrong, it outputs a 0, which is correct. Okay, so we obviously fed in not just one T matrix, but all 1,300 of these T matrices. And as we did, we kept updating the neural network in order to reduce the difference between the prediction and the actual reinforcement from the crowd. So far, so good? Okay, so we reduced that error. That's training. We were training the robot to make good predictions. Finally, the last step is testing. So I'm sorry, I misspoke. We didn't give the robot all 1,300 controllers. We took the 1,300 and we randomly picked half of them, which is our training set. This might start to sound familiar to you. We put those 650 controllers together in a training set. We took the remaining 650 and put it in our testing set. So these were controllers that the robot had never seen before. Once we had trained our neural network, we took those 650 T matrices and we pushed them through the trained neural network. And what are we looking to see now in the testing set? This should now sound very familiar to you.
accuracy.
Accuracy, right? How well did the robot do in predicting these novel experiences? This is our yardstick here. This is our measurement to see whether the robot has successfully grounded the symbol JUMP. Okay, let's see how it did. We did this for the simple robot and for the complex robot. The green here shows the average testing error on those 650 controllers. Lower is better. So on average, it was off by 0.42. Remember that the prediction ranges between 0 and 1, so it's not great, but it's pretty good, right? It doesn't get all the predictions correct, but it's starting to narrow in, right? Your system probably can't predict with 100% test accuracy, but you're getting close, right? Okay, so the question is, how good is 42? Well, we need to compare it to something. So we compared it to a permuted control. So what is a permuted control? Remember that we have these 650 or 1,300 T matrices, and associated with each matrix, we have a single number between 0 and 1. We took those 1,300 matrices and those 1,300
reinforcement signals, and we just permuted them. We just moved them all around. So we took the thumbs up and thumbs down, and we moved them from what their actual T matrix and attached them to another one and permuted it. So it's still the same data set, but it's all mixed up now. And since it's all mixed up, the robot does a worse job, does a worse job of prediction, right? So that means that, as we know, there's already data, there's good data in this data set. If we permute it, the robot can't predict unseen data as well. So it definitely is starting to ground these symbols. Okay, random control is we simulated a whole bunch of humans that just randomly did this for those 1,300 T matrices. And as you would imagine, the robots also do a pretty poor job of predicting. Make sense? Okay, we have, actually we're out of time, so that's perfect. All right, we will end there. You have a quiz due tonight. Your weekly report number 2 is due tonight, and we will talk about report number 3 on Friday. Thank you.